So welcome back, students. In this video we are going to start a new lesson number 8, Electromagnetic Waves. We are not going to study too much that is new in this lesson. It is also a very small lesson. This lesson is actually a synthesis of the first 6 lessons that you have studied. Not even the 7th lesson. The first 6 lessons, all that you know in the first 6 lessons are put together in this lesson. This lesson is a synthesis of those 6 lessons, all that you know about electricity and magnetism. The person who put this knowledge together was James Clerk Maxwell, a Scottish physicist, considered to be one of the greatest physicists of all time. He lived in the 19th century. He was also a brilliant mathematician. He came up with what is now called as the Maxwells Equations. But actually, those are not even his equations. Those are not new equations. Those are equations that you already know. He took 4 equations, 4 laws, I should say. Faraday's law, Ampere Secure law, and the 2 Gauss laws. One for electricity and one for magnetism. He took all those 4 laws together. And he found an inconsistency in one of those laws, specifically in Ampere Secure law. So since he was a brilliant mathematician and a physicist, he was able to tweak that law a little bit and put these 4 laws together. And when he analyzed those laws together, then he found something extremely wonderful and astonishing. A new discovery fell through these laws. It is like this. Suppose there is a bank robbery in your town, and you are the smartest person in town and a great detective, and the police ask for your help. And then what you do is that you collect all information regarding that robbery. You gather information about the time at which this happened, and how many people came, and what vehicle they used, and how much money was lost, and how they entered into the bank, and how they exited, and who saw them, and all kinds of information you collect regarding this bank robbery. So you analyze this case. As you analyze this case, suddenly you find that there is a link between this case and a murder case in Delhi. This is something like that. You try to put together some information, and then you try to analyze that information, and you stumble upon something else. And in Maxwell's case, that something else was the electromagnetic waves. What he said was this: well, if our knowledge about electricity and magnetism is true, if all that you have studied in the first 6 chapters of your 12th physics book is true, then electromagnetic waves must exist. What are electromagnetic waves? They are not the waves that we talked about in chapter 7. In chapter 7, we took this AC circuit and then we talked about the voltage input. V is equal to Vm sine omega t, and that is also like it's a sine wave. And you applied it to an electrical circuit and the current started flowing in the circuit. No, that is not what we are talking about here when we say electromagnetic waves. That is more like an oscillation. You supply energy and power to an electric circuit, and the power that you provide is limited to that circuit. You cannot get that power outside that circuit. The source is driving only the circuit. It's not driving anything else. So that is not what we're talking about. It's local. It's like oscillation. It's local. But a wave is something that propagates. A wave is traveling. It is traveling in space. It is propagating in space. So that is what he came up with. He said, if all these 4 laws are true, then my mathematics tells me that what you now call as electromagnetic waves must exist. They must travel in space without wires. It's like this. You are in a room and then you switch on the fan. Then the fan is revolving. So you get air and you're comfortable. And you know that you switch it on and then the fan is working now inside your room. Nobody else will know. Outside person, in the next house, they may not even know that you switch it on. There are no ways of knowing it. But what Maxwell says is that when you switch it on, there must be an electromagnetic pulse, a wave, that should travel in space. And maybe someone sitting in the Andromeda galaxy, many thousand light years away from you, a guy who is sitting on a planet which is going around a star in the Andromeda galaxy, so far away from you, may know that you have switched on the fan here. And this is what we mean by electromagnetic waves. They travel in space. And they fall through, they come through those 4 equations, the 4 laws that we've already come across. If we treat them mathematically, then this is a result of the treatment. It's there, it's hidden. This nature of electricity and magnetism is hidden in those laws. You just have to bring that out. That hidden nature has to be brought out through mathematical treatment. And he did this. So he said that electromagnetic waves must exist if these laws are correct. And those laws are correct, everybody knew, because they were working in other cases, so there was no need for anybody to suspect that they didn't work. They were true. Okay. So if those laws were true, then electromagnetic waves must exist. And he also said, by further treatment, a little more analysis, he said that light that doesn't seem to have anything to do with electricity and magnetism then must be an electromagnetic radiation from the sun. That's even more astonishing. You are connecting something which seems to be unrelated to electricity and magnetism is actually related to electricity and magnetism. So these are the things that he came up with. The electromagnetic waves was his prediction. Maxwell was born in the year 1831 in Edinburgh, Scotland. And then he died in the year 1879 in Cambridge, England. He lived for just 48 years. He died very young as per modern standards. Six years later, Heinrich Hertz was able to prove the existence of electromagnetic waves. Maxwell predicted that electromagnetic waves must exist, and Hertz proved that they do in fact exist. When Maxwell predicted, they didn't have the technology or the instruments. They didn't have a way to test his prediction, which came a little later, 6 years after his death. Hertz proved him right, but Maxwell did not live to see his prediction coming true. It's one of the sad stories of science. You predict something, you say that something must be true, something must exist. This is what must be happening. And there is no way you can prove to the world, because the technology has not been developed to that extent. You don't have the technology. And then somebody does this and proves you right, and you are no more. You don't live to see that you were actually right. As I said, it's one of the sad stories of science. With this introduction, we will get into the lesson. Let's start with the Ampere Secure law. So what does the Ampere Secure law say? It says that the closed loop integral of an open surface B dot dl is equal to mu naught multiplied by the current piercing through the surface. This is what it is. So the closed loop integral B dot dl of an open surface is equal to mu naught into I, where this I is the current which is piercing through that surface. So what it means is that if I imagine an open surface and suppose there is a wire with current I flowing through this, it's piercing through that surface. It's an open surface. Right? It's like a sheet or a bag or whatever. So like it is pierced. This wire is pierced through the surface. So at every point here, I'll have some B around this. There is current flowing through this. So if current is flowing through that, then there must be a magnetic field around it. So at every point on this loop, the contour of the surface, then you will have different B, right? B1, B2, B3, B100 or something. This will be B1 million, I don't know. So it's like that. You have lots of different B's, but if I do a B dot dl integration over this closed loop, then that must be equal to mu naught times the current that is piercing through the surface. The current should pierce through that surface. So that is the Ampere Secure law. So what Maxwell did was that he was trying to apply this law to a capacitor circuit. Suppose you are charging a capacitor. Okay. So you have a capacitor here. Probably drag there. You have a capacitor here. And then I am connecting it to a battery. Then what happens is that this capacitor C, this starts getting charged. Goes from 0 charge to some maximum charge. So as it goes from 0 charge to the maximum charge, there must be a current flowing. Right? So there must be current in this wire. So the charge I'll say take it like this. So current I is flowing through this wire. Since the current is flowing through this wire as it is charging, then there must be a magnetic field. Right? Because there is a current. For the current, you must have a magnetic field. So I must be able to use Ampere Secure law to this. Okay, suppose I want to find the magnetic field at this point P. This is my point P. Now I want to find B at this point. Right now it is getting charged. It is not done charging. Remember that. If it is done charging, then there will be no current. If there is no current, there will be no magnetic field. But now it is charging. As it is charging, then there must be a current. Since there is a current, there must be a magnetic field point in time. Okay. Now, let's see. If you want to find B, then what can I do? I can imagine a surface like this, right? And this is, I can attach a surface to this. I can imagine a circle, and then I can attach a surface to that. And you notice it is going to be at that distance, right? Like this would be the top of, this point would be the top point here. Now I can imagine a surface. Okay. This is not a surface. Let's imagine that I paste a paper. So then it becomes surface. Now this wire is going to pierce through the surface, right? So pierce through the surface, just like that. So what I can do now? I can do a B dot dl, right? I can do a B dot dl around this. If I do a B dot dl, around this loop, then I know that this is equal to mu naught into this I, because it is piercing through the surface. So this is how I calculate it. So I do this calculation, and I know this B dot dl must be equal to mu naught I. If I know I, if I know mu naught, and if I just take B as a constant out, then if you just do this stuff, so this is going to be, if it is the circle, then B is in the same direction as the dl. So B dot dl will become B dl, simply B dl cos theta is also cos 0. The 0 is the angle between the dl vector and also the B vector. So this will become that, and this must be equal to mu naught into I. Well, I also know this. B is constant. Like if we imagine this to be, the wire to be going through the very center, then this B must be the same as this B and this B. Directions will be different, but the magnitude must be the same. I know that. So I can take B out because it's a constant, because it's going to be the same for all points. So now this is 1, I can take B out, then I'm left with only B dl, and that's going to give me mu naught I. Okay. Okay. First, let me do this. Let me not worry about mu naught I first. Okay. Let me just do this integration. That's my integration. This is my I. B dl. So this is a closed loop integral. So it's a closed loop integral. So So you start from this point and then come back to that point. Then if I add all these dl's together, then I'm going to get 2 pi r. So this will be b into 2 pi r. Okay, so this is what I have calculated. This is my integration. What do I know from Ampere Secure law? This must be equal to mu naught times the current that is piercing through this. So at some point, I know what the current is, right? So this must be equal to mu naught I. Okay, I'll do it separately. So I say B into 2 pi r is equal to mu naught I. So now my B is simply mu naught I by 2 pi r. It's easy for me to do using Ampere Secure law. First I do this integration, and that integration must be equal to mu naught I. And if I know the value of I, then I know the 2 pi r, because this is the surface that I imagined. So B at this point can be formed like this. I can easily do this. Okay. Now I ask somebody else to do it. He does the same thing, except that he takes the same contour. Okay, this one. But then he is closing the surface like this. I use just a paper, right? I said paper, so it is closed like this is surface. And then I said the current is piercing through that surface. Well, Ampere never said that you must be using that kind of a surface. You need to use a flat surface or something. He said you can choose any surface. Doesn't matter. The surface can even be like this. This is also an open surface. If you notice, I start here, then come here. It's not closed surface. It's a closed surface, then this will also be closed. Now you see it is open. I can take this kind of a surface also. Now, if I attach this surface to this ring, that is also valid, perfectly valid. So this will sit on the ring. You know, the mouth of this bag can sit on the ring, and then I can have something like this. It's an open surface, right? It's open. It's not closed, not completely closed. It's an open surface. Think about it. Okay. So if somebody takes that kind of a surface, say in our case it could be Arvind. Arvind takes this. I've taken this surface. What Arvind says is Arvind takes this kind of a surface, and this is going to be his surface. It's a bag kind of a thing. This is open. But notice his contour is also the same. Yeah, now it's a bag. For me it was flat. For him it's black, but that is also an open surface. Instead of flat, then it has become kind of curved, but it's open surface again. But he will also do the same thing, right? This is because that is his mouth. That's a contour. That's a closed loop. You close the surface with this loop only. So what I did here, he will also do the same for his surface. Because the contour is the same, only the surface is different. So he will come up with the same integral, b into 2 pi r. And what will he say? Then he will come to do this. This must be equal to mu naught into I. Why? Because you see, even if it is a surface like this, the wire is still piercing through it. The wire is still piercing through it. So he will say, yeah, for me also it is I. For Swaminathan, it's the same I. And for Arvind, it's the same I. So he'll say mu naught I. So he will match with my integral. This is Arvind. And he will also match with my current. As for me also, the surface was pierced by I. For him also, his surface was pierced by the same I. So you will say, and for both of us, since the contour is the same, then we will do b into 2 pi r is equal to mu naught into I. Then b is equal to V naught I into pi r. So Arvind and I will calculate the same value. Now let's take Hari. Hari is going to use the same contour, okay, the same thing here. But then this surface, when he attaches that surface to this contour, he is going to take a bigger surface, a bigger bag kind of surface. Suppose this is his surface. So now notice that his surface goes into the capacitor. Okay. So what is his contour? Same as mine and Arvind's. All three of us have the same contour. Then when he does B dot dl, his integral will be this. He'll use the same logic. B dl cos theta, yeah, then B into 2 pi r is his integral. Okay. Now, he will try to figure out what is the current that is piercing through his surface. So his surface is this one. This is his surface. What is the current piercing through his surface? Well, there is no current piercing through his surface. The wire is not coming out of his surface. So what will he say? He will match with this as far as this part is concerned. He will do this integration. He will say my I is equal to B into 2 pi r because I have just taken the same mouth as us, the same contour as us. Okay? But he will say, well, there is no current that is piercing through my surface, so this is 0. And then he will calculate it and he will say B at this point is 0. I want you to understand this. I calculate value of B. I say this B naught I by 2 pi r. At this point, this is the magnetic field value. And Arvind calculates the same. Yes, at this point, this is my field value. And it matches with mine, irrespective of surface I take. My surface and his surface are different, but both of us come up with the same answer, just predicted by Ampere Secure law. Ampere doesn't care about the shape of the surface. As long as you do a closed loop integral of an open surface, you don't care about the nature of the surface. That's what he says. So both of us have taken the same contour. So this B dot dl must be the same for both of us. But then, and also the current which is piercing through us is the same. So both Arvind and I agree with this value. I say it must have, say, 1 Tesla. And then he also says, yeah, 1 Tesla. You're right. Yeah, I get the same answer. But now Hari comes up and says, no, it cannot be because you take this surface. I've taken this surface. As per my calculation, this is all right, but no current is piercing through my surface. So current which is piercing through my surface is 0. So this will be 0. So this is equal to 0. So B must be 0. He says there is no B at this point. There cannot be any magnetic field at that point. Is he wrong? No. As far as his mathematics is concerned, he is not wrong. He has done it perfectly. He has done the integration perfectly, and his reasoning that there is no current which is piercing through that surface is also correct. Just as Ampere asked you to do, he has done what Ampere has asked him to do. And as per that procedure, as far as he is concerned, there is no magnetic field here. But as far as our calculation, both Arvind's and my calculations, there must be a B here. And there is a B here. There must be a B. Why? Well, there is a current flowing through it. No, here there is the current flowing. There is a value of I here. So there must be a B. There must be a B. And Arvind and I come up with the correct answer. But Hari says that it is 0. He is not wrong. He has used the same procedure that I have used and Urban has used. All the three of us have used the same procedure. But two of us get one answer and the third guy gets a different answer. So that is a problem, not with his calculation, but with Ampere's second law. So that's inconsistency that we talked about. That's inconsistency that Maxwell realized. Depending on the surface you take to do this integral, the integral value changes. That's ridiculous, first of all. It cannot. It doesn't make sense. It shouldn't. But that's what's happening here. Then he asked this question, okay, then how do I fix this? How do I fix this? Well, there is no current flowing between the plates of a capacitor, clearly. Okay? And then you see here as the charge is changing. Okay? So at some point in time we will have a Q charge and Q1 charge, Q2 charge, Q3 charge, and then we will go till we get Qm charge. So at different points in time, the charge on the capacitor is changing. Then he asked this question. And what is this? What is this current? The current is equal to the rate of change of this charge here, right? The rate at which this charge changes must be equal to the current. So the charge is changing, so there is a current here. But there is no current inside. Then he asked this question, what is changing between the plates? What is changing between the plates? Well, think about it. What is between the plates? Between the plates, you have an electric field, right? So this is plus Q, and you will have minus Q here. So between the plates, you have an electric field. Will it be changing? You bet it will be changing. Why? You know that this E is given by this expression sigma by epsilon naught. We know it from our electricity chapters. The field between the two parallel plates of a capacitor is going to be E is equal to sigma by epsilon naught, and sigma is changing. Why? Q is changing. This Q is A is not going to change, area is not going to change, but Q is changing as you keep charging the capacitor. So sigma must be changing. Since sigma is changing, then E between the plates must be changing. You see, those lines, E lines, cross this surface, Hari's surface, the bigger bag. So the field lines change. Then he asked this question. Then the field lines are changing here. Okay? So remember Faraday's law? What did it say? It said that a changing magnetic field will produce an electric field. We saw that. An EMF was generated. There was an electric field. If I take a magnet and if I move it up and down, then there is an electric field generated. And if you have a conductor there, then the free electrons in the conductor will start flowing around. So a change in magnetic field produced an electric field. Then he asked this question. Here, the electric field is changing. Will it not be responsible for this magnetic field? If a changing magnetic field can produce an electric field, can a changing electric field produce a magnetic field? Then he went along these lines. So nature is symmetric. If something changes and produces something else, then if something else changes, then they should produce this. So if a changing magnetic field produces an electric field, then a changing electric field must produce a magnetic field. So even though there is no current through this, but the field is changing. Since the field is changing, then that must contribute to this. So once that is established, then this Ampere Secure law can be modified. The Ampere Secure law can be modified to accommodate this. Right now, what does Ampere Secure law says? It says only this. It says that the closed loop integral B dot dl of an open surface is equal to mu naught times the current that is piercing through it. That is one part. Now Maxwell corrects it. Yeah, that plus what he calls as a displacement current. Okay. So the Maxwell adjusts this. B dot dl is equal to mu naught I plus id. What does this id? He calls this as displacement current. Is it a current? No. It's a current equivalent. This is not current. This is a current equivalent. There is no current which is flowing here. This is a current equivalent. We'll tell you like how to get that. But right now keep in mind that B dot dl is equal to mu naught times I plus id. This is displacement current. When does the displacement current take place? It takes place whenever there is a change in electric field. Whenever there is a change in electric field, then you get a displacement current. If the electric field doesn't change, then there is no displacement current. So this equation is called as Ampere Maxwell equation. We will get to know how to do this ID shortly, but ID is going to use this ID that we have just discussed. The changing magnetic field should produce the change in electric field should produce a magnetic field. Just like a changing magnetic field produces an electric field, a changing electric field must produce a magnetic field. So with that idea, I am going to calculate it. But I am going to use this along with this. It's no longer I alone, I the current that is passing through it. Now it is equal to I plus id. Let's see like how it matches here. Let's look at this. Here, I take my surface. Okay, this is my surface, right? How am I going to apply Ampere Secure law here? No, Ampere Maxwell equation here. Well, B dot dl, I can do this. Yeah, no issues. And then this must be equal to not this, but B into 2 pi r must be equal to mu naught times I plus id. Okay, what is my I? Yeah, straight away this. But what is my id? What is my displacement current for my surface? I told you that the displacement current is not actually a current, but a current equivalent. And this would be calculated from the change in field, electric field. But look at my surface. Is there any electric field changing through my surface? No. There is no electric field changing through my surface. That is not being done. So for me, id will be 0 as usual. I will have only I, so then I will calculate B like this. This is how I will calculate. So, and Arvind, how will we calculate this? he will calculate this, all right, and then he will come here, and for him also I is passing through his surface. But is there a displacement current? Is there an electric field changing through his surface? There is no electric field changing through his surface. So he will also say that ID is 0 for me. So effectively, Arvind also will do B into 2 pi r is equal to mu naught to I. For him also, ID is 0 plus ID, that is equal to 0 for him. So he will also have this. So this is equal to mu naught I, this is equal to mu naught I. Okay? But now, let's talk about Hari. Hari will calculate B dot dl over the same ring, right? So B into 2 pi r, that doesn't change. Mu naught. Now, this is the surface. Is there any current going through the surface? No. So for him, this I is equal to 0. But then, there is this displacement current for him. So he will have mu naught to ID. This ID must be necessarily equal to I. We'll prove that later. Okay. So ID must be equal to I. So in that case, all the three of us will get the same value for B at this point, irrespective of the surface that we have taken. Instead of using this equation, if you use this equation, then all three of us, myself, Arvind and Hari, all three of us will get to the same answer. So this is the tweaking, this is the slight modification that Maxwell made to Ampere's Secure. So now this is called as Ampere-Maxwell equation. Is that clear? I hope it is clear to you. Now, we will prove that this ID will be equal to this I. If that is done, then everything falls in place. Now, I don't have to worry about the nature of my surface. So long as my B dot dl is the same, then I can attach a flat surface, a bag-like surface, or even a bigger bag-like surface, doesn't matter. It can go anywhere. Because the closed loop integral will be equal to mu naught times I plus ID now, not I. So, if I have I will not have ID. If somebody else has ID, then he will not have I. So that way, both of us are good, and both of us will calculate B at a particular point as the same number. Hope this is clear to you. So now, we will calculate the displacement current. We know what the Ampere-Maxwell equation is, just a modified version of the Ampere Secure law. The Ampere Secure law said that the closed loop integral B dot dl of an open surface is equal to mu naught times the current which is piercing through the surface. Now Maxwell has added a displacement current to that current. So now you have I plus ID, not just I. So now we are going to know the value of this ID. Okay, so that's what we will do. First, we took this circuit and then we said the electric field inside the capacitor is this. Then what is the flux, the electric flux in this space between the two plates? What's the flux? Electric flux phi E is actually E times A, right? Because the area is normal and E is constant. So if I do E dot A, then this will finally give me EA only. So A is the same, E is constant, and then we just take the E value and multiply that with the area, then I should get the flux, the electric flux. Okay. Then let's see. If this is the flux through the surface, see, that's the flux through the surface. Through Hari's surface. So what is EA? EA can be written as sigma by epsilon naught into A. But what is sigma? The surface charge density. So that can be written as Q at that point in time and then A, Q by A, that is sigma, epsilon naught into A. So this gives you Q by epsilon naught. So the electric flux phi E through this surface is equal to Q by epsilon naught. And we also know that Q on the plate is changing, so the field must also be changing. So let me do d phi E by dt. So d phi E by dt is equal to 1 by epsilon naught into this will be dq by dt. The rate at which this is changing. Okay. But what is dq by dt? dq by dt must be equal to this current I. How much this value is changing is what current is. So this is equal to I by epsilon naught. So this I equal to epsilon naught into d phi E by dt. And this is what I call as the displacement current. Is there a current flowing between the plates of capacitor? No, there is no current flowing between the plates of the capacitor. There is no current flowing through this surface. But there is d phi E by dt that is happening through this surface. The flux which is flowing through that surface is changing. The electric flux is changing. And that change multiplied by epsilon naught must be equal to I. And this is what I call as displacement current. This is also equal to what I call as ID. Is this an actual current? No. Displacement current is not current. It's an equivalent. This epsilon naught d phi by dt is ID. Displacement that happens to be equal to I. Here. Just like this is equal to this. So my ID, the displacement current ID is given by epsilon naught d phi E by dt. Okay. So now I can take this value and put it in here. So then Ampere Maxwell equation becomes this. It becomes integral, closed loop integral of the open surface is equal to B dot dl is equal to mu naught I plus mu naught epsilon naught d phi E by dt. Okay. I've expanded this. It's the same as this one. The same as this. It's easier to remember. But then you need to know the ID must be this. And I have put both of them together in this equation. That's all. I've taken this and put it in this equation and I formed this. Okay. So this is a displacement current. I want you to remember this. Displacement current is not actual current. This is the conduction current. I is conduction current. And this is displacement current. This part. You can see that it is not current. It is just the rate of change of the flux, the electrical flux through the surface, hurried surface. Okay? So there is no current there, but you call this displacement current, but this will have units of current. And you are combining this displacement current with the conduction current, I. I is actually the conduction current. This is conduction current and that is displacement current. And displacement current is not actually current, but current equivalent of the changing electric flux. I want you to understand this.